Hey everybody, today we are going to be doing Unit 6 of my AP Calculus review. This is on integration and accumulation of change. So we're going to be kind of focusing not really on derivatives anymore. I mean, we're going to a little bit now, well, not really today, but in the future we will for Unit 7 and a little bit of 8. We're going to talk still about derivatives, but now we're going to move on to a second, or maybe third if you include limits, the third big idea of calculus, and that's integrals, okay? So first, let's talk about what integrals are. So that's kind of the section. So this is a way of talking about the area under a curve. So let me show you what I mean. So we want to talk about this, and with our current geometry knowledge, it's really hard to find the exact area, right? But that's what calculus is for. We're going to use some tools to help us figure out what the area under this curve should be. Now exactly what is the area under the curve? Well, it's going to be all of this area enclosed here, right? And so basically it's just above the x-axis but under our curve. Now if our curve went below the x-axis, let's say, actually I'm going to hold off on that. Let me actually just draw another example here. Let's say our curve goes below the x-axis here, and we want to find the area between, I don't know, here and here. Well, we would just find the area like this, right? Between the curve and the x-axis, but this area here is negative. So we call it the signed area, so I'll say this is the signed area because it cares about the sign, whether it's positive or negative. This area here is negative, this little bit here is positive. Overall, since this area here is much bigger than this little area, we would probably have a negative area for this curve, right? But here it's clearly a positive area. So that's kind of what the integral talks about. So let's first take a step back and see, okay, well, how could we approximate this integral? Because approximations are a decent part of AP Calculus, so you should know how they work. So again, I'm not going to go into a lot of detail with these. I'm just going to kind of show you where these approximations come from, okay? So I don't want to make this video too long, but I want to make it so that you guys really understand what's going on. So if we want to approximate this, let me draw this again. Actually, let me erase this and then just draw it again. Okay, so basically we could break this up into a few smaller pieces, right? So, oops, I'm sorry, it's really hard to write at an angle like that, but I'm gonna say this piece, and we can break it up into this piece, and maybe this piece. So these are all equally sized pieces. I could have made them not equally sized, which is possible, but to make it easier for myself, I'm just gonna put them all as equal size. Okay, so this is cool. Maybe we could use an approximation for this, because if we try to approximate the whole thing and say, oh, this whole thing is a square or a rectangle, we would have a lot of extra area here. If we wanted to connect this endpoint with that endpoint, we would have a lot of extra area. But if we make these each rectangles or even trapezoids, that's fine. Yeah, it's not going to be exact, but it'll be a lot better. So the thing I want to tell you is basically that if you break up your piece into smaller and smaller pieces, it's going to make your approximation a lot better. And so with that in mind, try to think of maybe how could we make this approximation exact, into an exact answer. And the hint is that it uses limits. So we're going to get there, but I just kind of want you guys to be thinking about that. So basically what we're going to do is we're going to take these little pieces and kind of just approximate it. So let's say this difference here is 2. So we have 2 here, another 2, another 2, and another 2, right? And then this height, this would depend. So let's say this height here is 10, then this height may be I don't know, 7. This height looks to be about 6 maybe. This one would probably be about 8. That's a terrible 8. We put the 8 over here. And this height here seems to be about like 12 or something relative to everything else, right? Let me actually put that on the inside so it's consistent here. Right, so if we have these heights and we're trying to do a rectangular sum, we actually have two different options. So we could take, you know, we're gonna take the base times the height, but we can choose which height, right? Do we want to choose the 10 or the 7? And that really depends. So we have two options, and these each are very valid in their own senses. But what we're doing right now is finding what's known as a Riemann sum. And Riemann is the person that came up with this, and it's a way of approximating the area under a curve. So there are 4 different types. First off, there is what's known as the left sum. Sometimes you'll see it as LRAM. Typically it's said like a left Riemann sum. That you'll probably see that on the exam. I don't know exactly what this stands for, like left Riemann accumulation, I don't know, whatever. And then there's the right sum, which is sometimes denoted RRAM, RRAM. So let me just put these guys in parentheses. But basically, we could choose, right? So for the left sum, we could say, okay, well, we have 2 times the left endpoint, which is 2 times 10, plus 2 times, for this rectangle, we would choose the 7, so 2 times 7, plus, now we're doing this one, so we're going to do 2 times 6. And then finally, we're doing this one, which is 2 times 8. Okay, notice how we didn't include the 12, because, you know, we have 4 rectangles, we have these 2 different endpoints here, so we're doing all the ones on the left. So we would ignore the 12, right? If we do the right sum, you can do it in 2 ways I like to think of. You can start here and just choose the left one, or you can start here and choose the left one. They each, like, they're the same thing, but it's just like, it's your preference. Do you want to start here and do the left? And so you'll do 2 times 12 plus 2 times 8 plus 2 times 6 plus 2 times 7. Or you can just do 2 times 7 plus 2 times 6 plus 2 times 8 plus 2 times 12. It's up to you wherever you want to start, but it's going to end up with the same. And you can calculate these areas. They're going to be a little different. So I'm actually just going to calculate this. I just came up with these numbers, but yeah, let's calculate it. Okay, so I've got 62 for the left sum and 66 for the right sum. Now, I do want to notice that here the function is decreasing and then increasing up here, right? So on these intervals, you can notice that the left sum will be a lot bigger. So I'll do the left sum in, like, I'll just do it like that, and then the right sum, I'm just going to do it in like a dotted line, okay? So then the left sum here is going to look like this. I'm trying to do it as straight as I can. And the right one looks like that, right? The left one here looks like this. The right one looks like that. Hold on, let me make that a little better. The left one here looks like this, and the right one looks like that. Now the reason I want to talk about that is because you can see whenever you're decreasing, the left sum is going to be bigger than the actual area. You're going to have an over approximation. But whenever your function is increasing, your left sum is going to be smaller, and vice versa for the right sum, right? So whenever, so if your function is purely increasing or purely decreasing, it might be easy to figure out whether you have whether your approximations are an over or an under approximation. So just keep that in mind, because there are questions about that. So don't just like think like, oh, okay, I'll memorize it. It's good to visualize this kind of stuff and really just do a lot of problems, look at some past AP questions on like Riemann sums, and really just, you know, do a lot of practice, because obviously what I'm saying is not everything. There are 2 other methods. There is the midpoint sum. So I'll just kind of do this. So there's the midpoint, and there is the trapezoid sum. This is sometimes MRAM, and this is sometimes TRAM, okay? We have something like this, the midpoint sum, something like that, right? And we're saying we're trying to find the area between here and here, right? So let's say we have 3 equal sections here, roughly equal. Let me move this over a little bit. Something like that, right? These are kind of equal. So you can see, so if we take the midpoint of this interval, we're going to have this here, and so our height for that one is going to look like that, right? The midpoint for this interval is going to be, so it's going to go up here about, and our rectangle is going to look like that. And the midpoint for this interval is here, so our rectangle looks like that. And we can close off these edges. I noticed that this one's a little thicker, but that's okay. But yeah, you can see, like with the midpoint sum, that's how that works. And the trapezoid sum, so we just do something like that. So if we're finding the area between here and between here with 2 subintervals, let's say, so this trapezoid is going to look like that, this one's going to look like that, right? So our area is going to be this whole thing. And from this, it's easy to see that whenever your function is concave up, your trapezoid sum is going to be an over approximation. And conversely, if your function is concave down, if it looks like a downward opening parabola, you're going to have an under approximation for your trapezoid. And what's cool is that the midpoint is the exact opposite of that. So I want you to kind of just do some practice with that, familiarize yourself with that kind of stuff. But yeah, these are Riemann sums, and let me kind of give you the definition. Let's do, I don't want to use the midpoint and the trapezoid because they're kind of complicated. I just kind of wanted to show you how those work. But for, let's just do a left sum. It doesn't matter, you'll see why. So let me actually erase this as well. Essentially, an approximation, and I'm going to call this approximation A, and I'll just give that subscript L for the left sum. So this approximation is equal to the sum because we're summing up a bunch of things. And if you're not familiar with the sum notation, let me actually make this look nicer. That's okay. So just kind of bear with me for a little bit, or you can skip through to the kind of end of this section. But basically, I kind of just want to show you where the integral comes from. So let's say our index is n. So n goes from 1 to, I don't know, just some capital N. So this capital N would be that last endpoint. Actually, no, it would be this. We'll talk about it. So essentially, this is going to be an f of xn times a delta x. And you're like, whoa, what's all this? So pretty much, this f of xn, so this is telling us we're going from 1 to capital N, where 1 is this guy and capital N is this guy for that last rectangle. It's that left endpoint of the last rectangle. And so I'm taking f of xn, so f of this first, the x1, so it's going to be this up here, times that little change in our x, right? So it's going to be 2 times 10, right? And then for x2, it's going to be this guy here. We're going to do this times delta x. And then this guy times delta x. And then this guy times delta x. And this happens to be our last one. So that's pretty much what that means, right? So I hope you can kind of see that. So we're taking f of, like the function, the output of the function at that particular point, times that little change. So this is our left sum. The right sum looks very similar. It's just we're starting, you could say, you know, like x1 is here and then it goes to here. It really doesn't make much of a difference. So this is our approximation. But remember what I said earlier, that the approximation gets better and better whenever we split our interval into smaller and smaller, whenever we split, our interval into smaller and smaller subintervals. So what should we do? Well, what if we have an infinite number of subintervals? And you're like, whoa, where did that come from? What does that even mean? So we're not talking about exact infinity, because then these guys would have zero width. What I'm saying is that their width is so small that it's barely even there. So what I'm saying is that the integral, and I'll call this integral I, is equal to, so we're going to take this sum, we're going to say n equals 1 to capital N of f of xn times delta x, right? And we're going to say that it's going to be the limit as capital N approaches infinity. So capital N, the number basically tells us the number of subintervals we have. It's going to go to infinity. It's going to go really way up. So whenever we do this, this is exactly equal to an integral of f of x dx. And okay, so f of x, we no longer have an f of xn, right? Because it's just, now we're saying, okay, well, give me a function and I'll output you the integral, or the area, right? This dx is the same thing as this delta x, because delta means change. The only difference between these two guys is that dx tells you that it's a really small change, like basically almost zero. So that's kind of the information that this guy entails. And the bounds from here, right, kind of similar to this, we're going to be going from our first endpoint to our last. So technically we have from x1 to x capital N, right? But typically it's easy, you can just say it's from A to B. We like to keep things simple like that. So we're going from A to B. So I'm going to say this is A and this is B. And so basically all you need is A to B. This is the area between these two endpoints of this function. So give me the function, give me the endpoints, and I can give you the area. That's what this is saying. Isn't that crazy how we can just come up with this guy and it just works? What's even crazier is that, actually, let me hold that for a second. But yeah, so this is what an integral is, and this is the symbol. It's an elongated S. I've seen people kind of just go like S, and it's not great, but you can if you want. It's just better if you go like that, or something more straight like that. It's fine. It's best not to write an actual S. It's better if it's an elongated curvy S like that. Okay, so let's go into our next section about kind of different types of integrals. Actually, I did notice that this video is pretty long so far, so I'm going to cut it here, and in the next video we'll talk about the rest of what I wanted to talk about. So thank you guys for watching, and I'll see you then. Bye guys.